Hello, in this video we're going to talk about acids and bases, present in sections 10.3 and 10.10 of your book. So one of the first things we need to do is define just what an acid is and what a base is. People have written entire papers in educational journals of how best to describe to students what an acid and a base is. And so this table attempts to at least give some examples of how you can tell these things apart. So acids give you a sour taste or a tangy taste. Please don't go out and start tasting acids for fun. But if you taste vinegar or lemon juice, that's sour. The key component of sour gummy worms or sour candies like that is citric acid, which gives it that kind of sour, tangy taste. In contrast, bases taste bitter and tend to feel slippery. Soap is basic, and so that has its own special taste, right? Acids produce hydrogen ions when they're dissolved in water, while bases produce hydroxide ions when dissolved in water. Acids and bases will neutralize each other to produce salts in water. We have this stuff in chemistry called litmus paper, which will turn red with an acid or blue with a base. Or even better, we have multi-pad indicator paper, which will allow you to figure out the concentration of acid or base in a sample. And acids are reactive. They tend to produce gases with metals. Bases are also fairly reactive. Okay, and this is the best description we have, really, of acids and bases. Now, the chemistry between acids and bases is very critical. Your body is a big system that's very finely tuned to a certain level of acidity, and if that gets out of whack, then you die. So the slight changes in acidity can have a big effect on your body and many other chemical systems as well. In this course, we'll define acids and bases in two ways. The first way is known as the Arrhenius definition, and then we'll talk about the Bronsted-Lowry definition. So first, the Arrhenius definition. This is defined in water that an acid produces H3O+ when dissolved in water, and a base produces OH- when dissolved in water. Now, let me talk about H3O+ for a second, is that we chemists are often pretty lazy, where we should say H3O+, hydronium ion, because that really is what exists in solution. But often we just say H+ instead because we're lazy. And H+ is really just a proton, and a proton is too small to exist just by itself in aqueous solution without interacting with the water, right? So we say H+, really it's hydronium ion. So sometimes you'll see reactions written like they are up top, and this one's the better one. Ta-da! But you can also write this very same reaction as hydrochloric acid dissociates to form H+ and Cl-. And it's just a shorter way to write it. Really, it means the same thing. You're just adding or subtracting water to both sides, in effect. When I first started teaching, I used this shorter method. But then I realized, if I'm going to do this, I might as well do it right. And so now I give this method. But just keep in mind that you'll still see both of these very commonly. Okay, so that's the Arrhenius acid. Then an Arrhenius base produces hydroxide anion when it's dissolved in water. So sodium hydroxide produces Na+, OH-. So then in the Arrhenius definition, when we talk about a neutralization reaction, which is a reaction between an acid and a base, in effect we're saying, well, since the acid produces H3O+, it reacts with the base, which produces OH-, and this makes water. In reality, you put HCl in, which that makes the H3O+. You put sodium hydroxide in, that makes the OH-, right? And then you get water and a salt. But really, it's the hydronium and the hydroxide ions that are reacting together to make the water in the Arrhenius theory. And that works for a lot of systems, and it's pretty simple, so we still use it a lot. However, it does have some problems, right? Ammonia, when you put it in water, is basic, the NH3. And how is it basic? It doesn't contain an OH ion to release to the water. Sodium carbonate, sodium oxide are also basic, but they don't have hydroxide ions. When you dissolve carbon dioxide into water, it's a little acidic, which you might notice that if you ever drink a carbonated versus flat beverage. And that does not contain hydrogen ions to release, right? And then acid-base chemistry at times also works when you're not in aqueous solution, and this doesn't explain how that would work. So that leads us to the Bronsted-Lowry definition, which we'll talk about next. So here's the Bronsted-Lowry definition. A little broader. So here, the acid can donate a hydrogen ion, so it donates H+. And since hydrogen plus 1 is really just a proton with no neutron or electron, we call this a proton donor. So the acid can donate protons, then the base can accept protons. So here's an example down here. We have acetic acid, and acetic acid is written this way to show that this hydrogen right here is the one that can be donated, whereas these hydrogens here don't get donated at all. So looking at this reaction, let's define the acids and bases. So the acetic acid on the left, its name is kind of a giveaway. What it does is it donates that hydrogen to the water. And so then the water in this side of the reaction on the left acts like a base because it accepts that hydrogen ion. And then it forms H3O+, hydronium, and the acetic acid negative ion version, which is called acetate. Now that we have the definitions sorted out, let's talk about how to identify acids and bases. And so this works regardless of the definition you're using, just kind of a handy how-to guide for picking out these molecules so you can tell when you need to start thinking in terms of acids and bases. So a base is probably an easier one to see. It's an ionic compound with hydroxide as the anion that's soluble in water. So an example here might be sodium hydroxide, potassium hydroxide, things like that. Bases are also ammonia or compounds that have some component attached to an NH2 group. This will also function like a base. Acids, the easy ones to see are ionic compounds where the cation is H+. So you'll have an H first and then some anion you recognize, like HCl, where chloride is the anion you recognize, HNO3, where NO3 is the anion you recognize, things like that. And then there are a boatload of organic compounds that are acidic. The most common group you'll see is this C double bond to an O, single bond to an O that has a hydrogen on it, where that hydrogen that's on this oxygen down here will dissociate and come off and be the H+, and then you're left with this O- over here. So this group is called a carboxylic acid. That's the general name for it. We don't use that name in general chemistry, but we'll just call it instead by what the individual acid is. So this one here is acetic acid, which is the primary component of vinegar. Something that I'm going to tell you now, even though it's not present in this semester of the class content, is strong acids and bases and weak acids and bases. So what we do in this semester is we just say, all right, acids and bases completely dissociate in water. But that's not actually true. There's a lot of acids that don't do this. So the word strong is associated with the acids that completely dissociate in water, to the picture that we just were talking about. There's this whole category of weak acids and bases that only partially dissociate in water, maybe 2 to 3% split apart into the H+ and the rest of it, or form hydroxide, whatever they're doing. And then the rest of it stays together. And acetic acid is a weak acid. This is benzoic acid, C6H5CO2H, that is a common preservative in foods. Hydrofluoric acid is a weak acid. Nitrous acid is a weak acid. And then weak bases, ammonia, this is methyl ammonia, CH3NH3. So those are weak acids and bases. This definition between weak and strong acids and bases becomes really important when we start discussing acid-base equilibrium in the later part of this semester. Something else you should know about acids and bases is that they can be monoprotic, diprotic, triprotic, so on and so forth. And so monoprotic acids, they have only one proton that can come off of the overall molecule to form H+ in solution. So hydrochloric, nitric, acetic acid, those are monoprotic acids. They'll produce one H+. Now, sulfuric acid here, H2SO4, is a diprotic acid because there's two hydrogens here, and both of them are acidic to some degree. So you have one step where you produce an H+, and then you have what's called hydrogen sulfate left over. And then the hydrogen sulfate can produce another H+ and leave just sulfate around. It turns out that the first step here is strong, the second step is weak. And then phosphoric acid, H3PO4, can go through 3 steps and overall produce 3 hydrogen ions per formula of phosphoric acid. So this is something I want you to know, if only so that you understand what we mean when we say this is a monoprotic acid. Because we do say that when working problems, because sometimes you need to know that to be able to correctly do the problem. Okay, you just heard me naming acids, and I want you to be able to do this too, so that we can talk about the chemicals that we're using. So acid naming is unfortunately a little complicated, and so you have to pay attention to the cases and what type of acid it is that you're naming in order to be able to pull that off. So we have 2 major categories. One is simple binary, and so that would be where the anion is a halogen, so fluorine, chlorine, bromine, iodine, or the anion is cyanide or sulfide. And then we have a second category called oxoacids, where the anion contains oxygen, and we'll get to these on a subsequent slide. So the simple binary are down here, and what you do is you put the word hydro in front, and then you put the base name of the anion, and then you have a little IC suffix, and then you put a space right here, and then you have the word acid. So an example here is HCl. So this is hydrochloric with a space, then acid. Now keep in mind this is an acid when it's dissolved in water, aqueous. When this is a gas, which is hydrogen chloride just by itself as a gas, it's named like a molecule. For this thing to function as an acid, it needs to be in water. The forming H plus and OH minus thing only makes sense when you're in water, which is HOH effectively. And so if you have the molecule just as a gas, well then you name it like it was a molecule, like you would before. Now our second case is oxoacids. And with oxoacids, then you still have some decisions to make. If your polyatomic anion ends with ATE, then you put the root name of the anion plus IC, and then you put a space and then acid. Note that there's no hydro in front here. No. Okay, so you take the perchlorate anion, and this becomes perchloric acid. You take the chlorate anion, it becomes chloric acid, just like that. Now, another case here is if your polyatomic anion ends with ITE, then this becomes OUS instead of IC. Still space, still acid, same thing. You're just taking ite and turning it into us. And so an example here is the chlorite anion. This becomes chlorous acid. And then hypochlorite becomes hypochlorous acid. And so to keep these 2 cases straight, you replace ate with ick because you ate something icky. And those kind of seem to go together. Hopefully you didn't eat something icky, but sometimes you do, right? And then the ite us is, well, the other one. That's kind of how it goes in my head. You ate something icky, or ite and us go together. It works for me. Find a memory trick for you, and then use it, because this is something you'll need to know how to do. So some more examples of how to name these things. All right, on the left, this is CH3COOH, and the reference ion here is acetate. So this is acetic acid, because you take the ate and replace it with ick, and then you put a space and you say acid. Now then we have sulfate, sulfite, persulfate, and then I have kind of grayed out here hyposulfite, because it doesn't actually exist, but if it did exist, that's how you would name it. And when you're naming these acids, all right, persulfate becomes persulfuric acid. This one's a little bit of an exception. You would think persulfic acid, but that just doesn't sound good, so we call it sulfuric acid. There is exceptions in everything with language, right? And you'll use this enough to get used to it, because sulfate becomes sulfuric acid, and that's a very commonly used acid in the laboratory. You use sulfuric acid in the alum experiment that you're going to do sometime around the time that you watch this video. Now, sulfite becomes sulfurous acid. That's a lot less common in the laboratory, but it does exist. And then if SO2 formed an acid, this would be hyposulfurous acid. And remember, these are all oxoanions and oxyacids, or oxoacids, depending on how you want to say it. If you have something without oxygen in it, like in this case HCl, you put the hydro in front, so hydrochloric acid. No oxygen, you put the hydro in front. Okay. Now, acids and bases, when they come together, they neutralize, and they form a salt plus water. So this right here can be your mantra. An acid plus a base makes a salt plus water. Whatever it is, that's what happens. All right, so here we have the case of hydrochloric acid plus sodium hydroxide. Now, even though sodium hydroxide is a base, you still name it just like the normal ionic compound, so sodium hydroxide. So if you do the double replacement here, the H and the OH come together. So here's the H, here's the OH, and they make this fabulous compound called HOH, or water. And then the sodium and the chlorine come together, and they make sodium chloride. That squiggle didn't work. Okay, so then sodium chloride is soluble in water, so it's not a solid, it does not precipitate. Water is water. There's no saying that it's soluble in water because it is water. So we put an L after the water to show that it's a liquid. So that's the physical state for the water you make, is you make a liquid. Which makes sense because water is the liquid into which you're dissolving everything. All right, so that's the molecular equation here. So we can keep going and come up with an ionic equation where we dissociate all of the constituent parts. And to make this fit on the slide, I dropped all the physical states, which I would lose points on a test if I did this. So please keep the physical states whenever you're writing this out. But you have H+, Cl-, those are all aqueous, the sodium, the hydroxide, etc., etc. So that's the ionic equation. And then the reason why this works is because both HCl and sodium hydroxide are both strong bases and acids, so they do completely dissociate in solution and form these ions. All right, now these are the spectator ions that I'm crossing out here, and so we get a net ionic equation of H plus OH minus goes to water. Now, one of the powers of talking about a net ionic equation is that the same ultimate outcome happens if you have sodium hydroxide or potassium hydroxide. If you have hydrochloric, hydrobromic, hydroiodic acid, you still have the same net ionic equation because ultimately the same thing is happening. It's just the extra ions in solution are not changing. So talking about net ionic equations really does make sense here. Okay, so have you ever made a volcano or one of these kind of kindergarten or elementary school things? So the reaction you're doing here is taking HCl, hydrochloric acid, and sodium bicarbonate, which is baking soda, and you mix those together. And here I'm showing this with hydrochloric acid. If you ever do this at home, you're using vinegar, and that's fine. Vinegar is acetic acid, and it still works to make this reaction happen. And so then when you swap the partners here, you get sodium chloride, that's salt, and then you get H2CO3, which is carbonic acid. Now, the thing about carbonic acid is that it readily decomposes to water and carbon dioxide. And so this is what happens in your volcano that you make, is that the acid and the baking soda mix together and ultimately make a bunch of bubbles. And those bubbles are carbon dioxide gas being evolved from the solution. Fun vocabulary word of the day. A gas is evolved from a reaction. It comes out. Okay, that's what we have for now. Thanks for watching.